today, as you guys can see, it's another day. So I slept very well. I ate the Brazilian barbecue. If you don't know what Brazilian barbecue is, I hope you Google it and you try it. I have 2 places here in Colombia to do that. So it's basically all you can eat meat. So I'm very full of meat. Probably I don't eat meat from the last 10 days, or the next 10 days, but I'm still going to eat it anyway. And let's get into our Six Sigma metrics. So we're going to have 4 Lean Six Sigma metrics for discrete data, right? So remember, on our last set of videos, I talked about Six Sigma metrics with continuous data. Now it's Six Sigma metrics with the videos that I had, like the yellow shirt. And now it's about Six Sigma metrics with attribute data, okay, or discrete data. So we're still calculating the defect, the PMO. That's the most important metric in Six Sigma. If you're going to talk to Six Sigma people, they're all about DPMO. DPMO here, DPMO there. That's important. So KSigma levels and defects per unit. Okay, so we're going to see how to calculate them in this example. So in this example, Star Coral Inc. manufactures a backpacking tent called Stargazer, and to complete that, we can have any one of those following defects. So 1 or more of the 4 poles cannot be formed appropriate length. 1 or more of the 6 tent seams is inappropriately weather sealed. The tent door is inappropriately attached. The tent window is inappropriately attached. Or 1 or more of the 2 zippers fails to function, right? So what you need to do here is to understand, okay, we have all these points that we look in a tent, okay, and we can see that a tent can have a bunch of problems, right? So I need to understand how many problems or defects can have in total, possibly. So that will be the maximum number of problems, right? Or maximum number of quality defects. That we're going to call it defects per unit opportunity. Okay. So DPUO is the maximum number of defects. As you can see by what was written before, you can have 4 poles not formed, up to 6 seams not sealed, 1 door, 1 window, and 1 zipper fail. So the maximum amount of problems they can have is 14. That's the defect per unit opportunity. Okay. To calculate the DPMO, I'll open here your class notes. So the class notes has additional information here that the control quality department has just sampled 50 tents and observed 8 tents had defects. The number of each defect is here in this table. Okay, so this table tells how many defects on these 50 tents. So poles, we had 4 defects. Tents seems to have 3, 1 door, 1 window, and 2 zippers. Total number of defects that we found in 50 tents, right? So 50 tents, we found 11 total defects. Okay, so how do I calculate the DPMO? So you're going to take the total number of defects, which is those 11 that we have on the table, and divide by the maximum or the total number of checks that we did, which is the total number of possible defects, right? So we know that we checked 14 things in each tent. We know that we sampled 50 tents. So this is how many were actually checked. And from these that were checked, 11 were how many actually had problems. So you're just basically calculate a percentage, right? A percentage of defects divided by a percentage of total checks that we did. And all that times 1 million, right? I probably need to fix this formula here that doesn't look that good to do like this. Okay, now we're good. Save it. And yes, just in time fixing. So if we do that, we're going to get that the DPMO, defects per million opportunity, is 15,714. Okay. The KSigma level. So the KSigma level, remember that is the, oops. Esse KSigma level tá errado, não é mais. Ah, esse aqui é. Hello. So now we go to the KSigma level, and the KSigma level, so we're going to use again the norms inf that we used before. So in this case, what we have is the percentage level of defects, right? And from that percentage, we need to go back and calculate that in sigma levels, okay? So we need to backtrack what we did a little bit different than the continuous data, right? So it's going to be norms inf 1 minus the DPMO divided by 1,000,000. Remember, to calculate the DPMO, we multiply by 1,000,000. Now we're dividing by 1,000,000, basically getting the percentage, right? So that's the percentage of defects that we had. That's this thing. 1 minus that is going to give me the left area, right? So remember that we did 1 minus in the other equation as well. And then we're going to add the 1.5 shift, okay? So, and I will explain why is it different than the other one. So norms inf 1 minus this small area is going to be this big area, which is 98.43%. And then we do the norms inf, or what is the other way to do that instead of norms in? Look at the z-score table, right? So I don't remember if I mentioned that or not. You have the z-score table in page 67 of your notes, right? Here it is for you guys to glance. Maybe put it in your fridge, right, or on your closet door, so you can study and have it available for you any time of the day. And in this case, since we're in discrete data, we're going to add the shift. Okay, what is the logic there? And the other one, we basically said that, you know, the shift will make things worse. And for this one, we're saying that the shift will make things better. Your sigma level will increase. How does that make sense? Well, because it's a percentage, right? Remember, it's a discrete data set. So what's going to happen with that distribution? The distribution will go to the left and go to the right and go to the left. But whenever it goes to the left, you're actually creating less defects, right? Because the lower percentage level will be better for you, the higher percentage will be worse. So to account for this shift to the left, that number of standard deviations actually increase, actually becomes a better process. Okay, so does that make sense? Because the other one was a continuous. So when you go to the right or to the left, you are always creating more problems because the area outside the limits will be increasing. For discrete, one side is increasing, the other side is decreasing, actually, the number of problems. So at the end of the day, it is becoming better. So if you have a 2.5 sigma level, and with the shift, you actually have a 3.65 sigma level, which is actually better. Okay? Finally, I put everything in one video. It is the defect per unit. Okay, so you calculate by taking the total number of defects here divided by the tenths sampled. So we have 50. We collected data from 50 tenths. We had 11 defects, right? That's the number we calculated at the beginning there. So we have, on average, 0.22 defects per tenth. Okay. The last thing that we're going to calculate is the percentage of defective tenths. So that's the 8 tenths that had defects divided by the 50 that were sampled, right? So 16% of the tenths had problems. 16% of the tenths had at least one problem, right? Could be more than one problem, right? So we had actually 14 problems. So some tenths had more than one problem. Okay, and just to finalize, I'm going to take a look and show you guys how to do this in Minitab in our next video. You have here the support videos for Minitab. So you go here. There's a way to explain the book also talks about, the Brooks book talks about how to do things in Minitab and explain things in Minitab, okay? So you have these 2-3 resources to take a look to know how to do that.